The next step is, now that we have the configuration, we want to dive into the controller, the design of the controller. And the first step in the design of the controller is the feasibility of the noise requirements. If we cannot achieve the noise requirements, then there is no solution whatsoever, because feedback will not do nothing with the noise. It is an error reduction technique, but it doesn't reduce the noise. It can only make the deterioration of the signal to noise ratio as low as possible. So let's see what we are going to do here. So here we have to do the feasibility of noise and maybe temperature offset and bias current, which we can model them as equivalent input noise sources as well. We can do it all with SlickUp as simulator, and what we are going to design is basically the controller input stage, and the design aspects are the width, the length, and the operating current of this stage. So there's some interaction. You see here a dot, a blue dot on the roof, which means that the column number 2 and number 3 have a interaction, which means that the feedback network has some influence of the noise performance. You know, if we do non-inertic feedback, that influence is not there, but if we have passive feedback, then the feedback elements may be noisy themselves, or they enlarge the contribution of the equivalent input noise sources of the controller. And that's why the steps cannot be completely regarded as independent. So that's we put here the blue dot on the roof. So if the frequency range of interest includes temperature variations, the frequency of temperature variations, then we have to account also for those effects, but this was not relevant for the antenna amplifier. And if it is not relevant, we can just consider temperature influences at a later stage of the design. So the design of the active antenna, this is the task. We need to design a CS stage with a sufficiently low noise performance, and we need to determine basically the values for the current, the length and the width, and the number of transistors, the multiplication factor, or the number of fingers, whatever you want to specify there. So let's go to the active antenna. The CS input stage design, a short recap of that one. The antenna was capacitive, so we model it as a capacitor. What we had specified initially was the input noise in the domain of the electric field, so in volts per meter. So here is a converter from volts per meter to volts, which is set by the length of the antenna. But we are going to calculate in this example here the source referred noise at the location of this controlled source, the output of the controlled source. So you have to divide by LA to have it at the location of V1. We do that with the simulation, but we didn't do it in the calculation, but because for the optimum it doesn't do much. So the source referred noise at the output of E1, that is what we are interested in. And here we have a model representing the noise model, the noise of the NMOS as a function of the drain current, the gate current, the width, and the length. So we have to design those things. And since the gate current is assumed to be extremely small or 0, we just ignore it here. And we are going to find values or ranges for the current, the width, and the length, so that our total source reverse noise is low enough. Well, here was the expression. Maybe you remember. It was like 4kT n gamma divided by Gm times 1 plus the ratio of the total input capacitance of the FET divided by the source capacitance, and that totally squared, and then we had the 1/f noise. We found in studying the model of a transistor, for MOS transistor, that the corner frequency of the 1/f noise is proportional with Ft. So we can use that and just put that proportionality factor, whatever it is, in the expression, and Ft was GM divided by 2 pi CISS, and in this way we can find an expression for the 1 over F noise in this way. And you see this expression has an optimum. It has an optimum for CISS equals CS. So it means, and it is a minimum, that if at this optimum our 1 over F noise is too much, we have a showstopper. And we have a specification for the 1 over F noise of the antenna. So we are going to study this optimum and see if it is low enough. That's what we did. The floor, there's floor noise. That should be floor noise. The floor noise, we also had a specification for that, was set by GM mainly, but also you see the ratio of the capacitors there. So this can, in worst case, if we are going for the lowest 1 over F noise contribution, this can be a factor 4, 1 plus CISS over CS squared in total. This can be 4, but from a design point of view for the floor noise, we would like to have CISS much smaller than CS. So the order of in our investigations is first see if for low frequencies with the optimum our noise, 1 over F noise, is low enough. If that is low enough, then we can maybe make it a little bit larger to keep this CISS over CS as small as possible. And of course, CISS is also related to GM because both they depend on W, but GM can be made independent of CISS by increasing the current. So we use the current as a degree of freedom to make the floor noise as low as possible. Well, this can be done easily with slide cap. So here you find the result of an automated routine in slide cap doing this for you, and you see there were 3 cases with different inversion coefficients and different currents and W and L, but every case had CISS equals CS. So this is not necessarily what we are going to do at the end, but this was just to show that this optimum, that this works. And the 3 cases were, 1, we had a width of 1.2 millimeter, a length of 1.25 micron, 1.4 milliamp, and we found a floor spectrum at the antenna of 2.8, so 28 atto volts squared meter squared per hertz, because this was antenna referred. It says here at the picture source referred, but it should be antenna referred. And the corner frequency was 33 kilohertz. We could have a corner frequency as low as 100 kilohertz. So there is no showstopper, appears to be no showstopper here. This is the first estimation. This should be 2.5. It is 2.8, but with a little bit more current, it's easy, we can easily optimize this. And here we have another one. Another situation about the same result. You see the results are the same, the plots are on top of each other, but we have a smaller width, a larger length, so that the input capacitance is the same, and we have a much higher inversion coefficient. So it is not necessarily true that with this capacitive source here, that a low inversion coefficient is required for a low corner frequency of the 1 over F noise. You see, they all have the same corner frequency of the 1 over F noise. So this concludes the noise design. So we have ranges for W, L, and for the current. And we see that the results or the specifications can be satisfied. So that's what we need at this stage. We have no showstopper, so we can go on with the design.